going to continue talking about trig substitution problems. This one you'll notice is a definite integral. It's got the integral from the square root of 3 to 2 of the square root of x squared minus 3 over x with respect to x. And again, we've got that square root of something with an x squared in it, and I don't see any way that we can use an algebra trick to get this to be a basic formula, so we are going to want to do a trig substitution here. Now this one happens to be in the u squared minus a squared format, which means that we want to use u equals a secant of theta. So in this case, we'll have x equals, and be careful with this, remember this is a squared. So if a squared equals 3, then a is the square root of 3. So we'll have u equals the square root of 3 times, x equals the square root of 3 times the secant of theta. So just like always, I want to go ahead and divide to where I just have secant theta on one side, x over the square root of 3. And the rule for secant of theta is that this is the hypotenuse over the adjacent. It is the reciprocal of cosine. So when I build my triangle with theta, the hypotenuse will be x and the adjacent will be the square root of 3. And you'll find that if you use the Pythagorean theorem, you get that square root x squared minus 3 here, and you can verify that if you need to. Okay, so from here we're building our integral. Now the important thing about doing any kind of integration with a definite integral, anytime you're doing any u substitution, you have to take care of the bounds very carefully. And you have two options. You can either convert the bounds to u at the to theta at the beginning of the problem, or you can go back at the end and just convert everything back to x and use your new bounds. And it's up to you how you want to do it. I'm going to show you both methods. Just be aware you do have to deal with it one way or another. So for method 1, we're going to convert our bounds to theta. So the way we deal with this, if x is equal to the lower bound, the square root of 3, plugging that in here, x equals square root of 3 secant of theta, that would give me square root of 3 equals the square root of 3 secant of theta. And another way to say that is 1 equals the secant of theta. And since 1 is understood to be 1 over 1, and secant of theta is understood to be 1 over cosine of theta, that gives me that cosine of theta equals 1. Theta is going to be the cosine inverse of 1, and the one that we want for that is theta equals 0. For x equals 2, we'll have 2 equals the square root of 3 secant of theta. Dividing by square root of 3, we get 2 over the square root of 3 equals secant of theta, and taking the reciprocal, we get square root of 3 over 2 equals cosine of theta. So theta is the arc cosine or the inverse cosine of the square root of 3 over 2. And whatever way you need to do this, I recognize square root of 3 over 2 as one of my special 30, 60, 90 triangles. So, which has the 1 to square root of 3 ratio. And it looks like the one that gives me square root of 3 over 2 for the cosine is the 30-degree angle, or pi over 6. You could also use the unit circle. So what I'm going to do then with this method is I'm going to, when I convert this, I'm also going to replace the bounds. So we still kind of have to go through that same process. If x equals the square root of 3 secant of theta, then dx is going to be the square root of 3 times the derivative of that, which is secant of theta, tangent of theta, d theta. The other piece that we need is just a plain old x, which we have, and we need the square root of x squared minus 3. So the side that uses numbers would be the tangent. So the tangent of theta is the square root of x squared minus 3 over the square root of 3, which gives me the square root of 3 tangent theta is equal to the square root of x squared minus 3. So when I go to convert, my integral was originally the integral from the square root of 3 to 2 of the square root of x squared minus 3 over x dx. I will now have the integral from 0 to pi over 6, because we're changing our variable, so we changed our bounds, of the square root of 3 tangent theta, that's this part right here, over x, which is the square root of 3 secant theta, dx, which is the square root of 3 secant theta tangent theta d theta. And I'm going to integrate that. So I will cancel what cancels. It looks like we can cancel here and here. And I really have the integral from 0 to pi over 6 of the square root of 3, which will bring out front, tangent square root of theta d theta. Now this should hopefully look familiar to you. It is one of those even positive powers of tangent. It happens to be squared in this case, so we don't have to separate out one of them, but we're just going to convert it to secant squared of x minus 1. So this will be the square root of 3 times the integral from 0 to pi over 6 squared of theta minus 1 d theta. And then these are both things that we can integrate. We get the integral of secant squared of theta is just tangent of theta. Of minus 1 is minus theta. And that all goes from 0 to pi over 6. So we get the square root of 3. We'll have tangent of pi over 6 minus pi over 6. And then we'll have minus tangent of 0 minus 0. Tangent of pi over 6 is 1 over square root of 3. And tangent of 0 is 0. So multiplying that out, we'll have square root of 3 times 1 over the square root of 3 minus square root of 3 times pi over 6, which gives me 1 minus root 3 over 6 pi. And that is my answer. Method 2, which is personally my favorite method, if you don't like to convert your bounds at the beginning, you can convert everything back to x and then plug in the bounds. Now I'm not going to go through the whole problem from start to finish because we've done most of the work. But we started with the integral from the square root of 3 to 2 of the square root of x squared minus 3 over x dx. And following a trail of events, we wound up at the integral from x equals 0. And notice I'm making a note that these are bounds in x to x equals square root of 3 to x equals 2 of what ended up being tangent squared of theta d theta with a square root of 3 stuck on the outside. And you can see, follow all of that we did here. And then we integrated, and we got the square root of 3 times, it wound up being, tangent of theta minus theta. And that was all from x equals the square root of 3 to x equals 2. So at this point, if you would rather do it this way, you can convert back to x using your triangle. And let me just grab a copy of our triangle so we can see it. That's right here. So the tangent would be the opposite over the adjacent, which is the square root of x squared minus 3 over the square root of 3. The theta, you can use whichever one of the trig identities or trig functions that you want. I'm going to use maybe the secant because that has an x and a square root of 3. I'm going to go back actually to the original substitution, which was x over the square root of 3 equals secant of theta. So we'll call theta the arcsecant or the inverse secant of x over the square root of 3. So I'm just going to plug that in. And we will now evaluate that from square root of 3 to 2. So from here, I get the square root of 3. And I'm going to go term by term. We'll have, for the first part, we'll have the square root of 4 minus 3, which is 1 over the square root of 3, minus the square root of square root of 3 squared is 3 minus 3 over the square root of 3. And then the second part, we will have arcsecant of 2 over the square root of 3 minus the arcsecant of square root of 3 over square root of 3, which is 1. So I have square root of 3 times 1 over the square root of 3 minus 0 minus the arcsecant of 2 over the square root of 3. Again, going back to your 30, 60, 90 triangle or your unit circle, whichever one you like, that gives me pi over 6. And the arcsecant of 1 is 0. So you can see that you get 1 minus root 3 over 6 pi, just like you did in the previous method. Now, they're not all this convoluted. Sometimes it'll be more simple to do it one way or the other, but honestly, it's the same amount of work either way. It's just, do you want to do that work up front and convert your bounds, or do you want to do that work at the back end of the problem and just deal with it at the end? It's up to you. This last example shows a problem in which we don't necessarily see a u squared minus a squared or u squared plus a squared, but we have something that could be converted to that. Now, your first instinct is probably to try to make u be x squared minus 2x and make this the integral of u to the 1/2 du, but the problem with that is that you would need 2x minus 2 to build your du, and we don't have it, so we can't really do that. That's not valid. So what I'm going to do is I'm going to complete the square, and there are many, many, many videos on how to do this if you've forgotten. I'm starting off with x squared minus 2x. My b is the negative 2, so 1/2 b is negative 1. So I'm going to add negative 1 squared, and then I'm going to subtract negative 1 squared. So this part gets factored to be x minus 1 squared, and then we have minus 1. So now what we've done is we've created a u squared minus a squared where u equals x minus 1 and a equals 1. So we can use the substitution u equals a secant theta. So x minus 1 equals 1 secant theta. Or another way to say that is secant of theta equals x minus 1 over 1. And of course that leads us to a triangle where the hypotenuse is x minus 1, the adjacent is 1, and the other side is the square root of x minus 1 squared minus 1. And this is important to understand. When we complete the square, our integral is now the square root of x minus 1 squared minus 1 dx, because those are equivalent. So now I've got to make some substitutions. I can see that we know that x minus 1 equals secant of theta. So x is going to be 1 plus the secant of theta. Dx would be 0 plus secant of theta tangent of theta. D theta. Or just secant of theta tangent of theta d theta. And then for the square root, we're going to use the opposite in the adjacent. So tangent of theta is going to be the square root of x minus 1 squared minus 1 over 1. So this is now the integral of tangent theta times secant of theta tangent of theta d theta. And that's what we're going to be integrating. So all of that background work to get to there. This is the integral of tangent squared of theta secant of theta d theta. And again, you should recognize that from the previous section where we looked at these different cases. keep in mind any of these sine, cosine, secant, or tangent rules may apply. So this is one where we had a tangent squared and just a regular old secant. So I would probably take the tangent squared and convert to a secant squared of theta minus 1. Where did it go? There it is. So I would have the integral of secant squared of theta minus 1 times secant of theta d theta, and that goes here. So when I distribute, I get secant cubed of theta minus secant of theta. And I'm going to split that into two separate integrals. Now, the integral of secant cubed of theta is very, very complicated, and on a timed test, I'm not going to throw that in the middle of a problem, or at least I don't plan to. But this comes from 8.2, from section 8.2, and it uses the integration by parts, and you find that that gives you, let's see, that gives you 1/2. We get secant theta tangent theta plus 1/2 times the natural log of the absolute value of the secant theta plus tangent theta. So all of that is just the integral of secant cubed of theta. Again, go back to section 8.2 and you can see how we come to that. Now this part just integrates to be minus the natural log of the absolute value of secant theta plus tangent theta. And of course, all of this is plus c. So the nice thing about it is this is gone. Well, not gone. It is going to combine. Because you can see they are the same. They are like terms. So we'll get 1/2 secant theta tangent theta minus 1/2 times the natural log of the absolute value of secant theta plus tangent theta, all plus c. Now at this point we have to go and convert back to x's. So look at what we've done previously. We know that x minus 1 equals secant theta, and we know that tangent theta is equal to the square root of x minus 1 squared minus 1. So I'm just going to plug those things back in. So I'll have 1/2 times x minus 1 times the square root of x minus 1 squared minus 1 minus 1/2 times the natural log of the absolute value of x minus 1 plus the square root of x minus 1 squared minus 1, all plus c. And that will be my final answer. Now keep in mind, like I've said, I've shown you some of the scenarios that can come up. When you're doing a trig substitution problem, any of the valid trigonometric integrals that we've looked at, either from section 8.3, the section 8.2 secant cubed of theta, or your Cal 1 basic rules for all of the trig functions involving, or all of the functions involving trig functions, any of those are fair game. They could show up as part of the end when you have to actually integrate, and then when you have to convert to x. So as you go along, if you start doing some research on this, or start trying to look up something that you haven't done in a while, you may see some special forms that get used quite a lot, and these are 3 of them. They usually appear in just about every integration table that you find. I don't recommend that you try to memorize these. I recommend that you go through the process, because the process is a lot easier to remember than all of these little sticky details about what goes where. But if you look in a table, you will see these formulas, because these appear quite a lot.